Okay, hello everybody. How are you doing? Thank you for your patience. I'm a little late and a little technical difficulty. It's our last time together before spring break. I hope you're having a little bit of time to rest in the next week. Administratively, there will be the preliminary outline due the Monday, 11:59. And on that Tuesday of spring break, that'll be the 24th, there will also be a lab. I haven't released the lab yet, but that'll happen pretty soon. Any questions? Yes?
So for the preliminary outline, like but there's also a field that would be assigned to submit the outline.
Yes. Yes, but it should be a group project now, right?
Yeah. So is the idea that a process is the one to be assigned on there?
Right, if that's how it should work. Okay, but everyone, so your name again is? Jesse, yeah. So what Jesse is asking is, does everyone need to do this survey? Yes. Okay. Is there a code for this one? No. Is there one link that everybody should make sure is in their group project submission? Yes. Does that make sense? Okay. So there's no code, but everyone needs to complete the survey. Okay. Yes.
I guess I meant like the surveys, yeah, like I understood that, but the actual assignment, where you put the thing in and put submit this.
Yes.
So is that meant to be like each person, what's the link to takes the link to the document to the field in the assignment, like similar to how you do a lab?
I think, so actually, this is where I will confess. This is the first time I'm using groups, okay, for the class. Before, I had everyone just do an individual one. I'm hoping that this makes it simpler for all of us. Okay, so the idea, I thought, was only really one person had to submit that link for the group project. If I am incorrect on that, we will find out very soon. Okay, and I'll send out an announcement. So thank you. All right, but it's yes. What if you have an insight?
In the form, there's like something to fill out on a title, this is actually your
That is a mistake. Thank you for pointing that out. Yes, that should say, I want the working title, and the URL is there too. So I need to choose which one I want, right? But yeah, you can also submit, so I'll go and I'll fix the survey, all right? But I think we'll be on the same page. Make sure the URL goes into Canvas. Okay, good, good, good. All right. So, any other questions? All right. Today we're going to, I think we're going to end early, okay? With us, if you want to talk about your final project, I'll hang out afterward, okay? But I think we should have time for that based on the amount of material we're planning to cover. And then that which we will cover includes a couple of physics, residuals, and then a little bit on the final project, okay? And some time for that. So this is kind of the plan for today. And just a reminder that the preliminary outlines are due on Monday. So here we go. This course is named Multiphysics Simulations. And, well, we are going to be we're starting to deal with multiple types of physics. And sometimes these physical phenomena are going to be interacting with each other. They're going to be coupling with each other. So let's revisit what we've done a little bit up to this point. Okay? And let me just delete that. Did we have coupled physics in these previous examples? Were there multiple domains of physics? When I say domain, okay, so domains often refers to, the meshes or the nodes, okay? But in this case, when I say multiple physics, I'm saying more or less, did we combine one subject of one of your courses with another subject of one of your courses in mechanical and aerospace engineering? So, for example, were there problems that we've done so far that have required knowledge of thermodynamics and fluid mechanics, or heat transfer and fluid dynamics? Were there problems that required a coupling between fluid mechanics and mechanics of materials, or solid mechanics? What do you all think, based on what we've done so far? There's not necessarily one answer. I want to hear what your thoughts are and why. And as a reminder, right, we have some examples here where we're looking at a turkey, all right? And we have an example now with flow over a pipe. So what do you all think? Or any other examples? Sure.
I just put these two on the board right now. I just
Okay. Okay. All right. So let's extract that a little bit. Okay. When we started using the Neumann boundary condition for the turkey, I can say you're right, and I'm also going to say, well, let's talk about it a different way, right? So yes, we kind of try to stick to one kind of subject, right? Fluids, heat transfer, right? When we did the Neumann boundary condition, and I guess, well, we also had, particle dynamics and all that stuff too, right? Molecular dynamics too. But in terms of discretized meshes, we've talked about how you had the Neumann boundary condition about a turkey. Now, what is the Neumann boundary condition? Yes, Mia.
It's like the first derivatives.
It's the what?
It's like the first derivatives.
Yeah, so the first derivative, right? And so in the case of the Neumann boundary condition for the heat equation, what are we specifying? What does that first derivative correspond to? Yes?
Like a flux.
Yeah, heat flux. Heat flux in. And or we could say it's got 0 there, the first derivative of the temperature with respect to time or space is 0, and so that means that if that heat flux is 0, that's an insulating boundary. And the Dirichlet condition, right, was temperature. Well, when we did, if you remember, when we did the Neumann boundary condition, or we applied the Neumann boundary condition to the turkey problem, what did we say was happening to that boundary? Okay, where was the turkey, first of all? And what place physically were we imagining putting our turkey? Huh? What were we going to say? Oven, right? It was in the oven. Okay? And so it's in the oven, and what's happening in the oven? With the surrounding fluid. Hold on, yeah. Someone else, yes. Right, so you've got this object, you've got heat, and you've got a cold object, and you've got a warm air, you've got gravity, right? It's probably hotter on the bottom than it is on the top when it gets to the top after it's gone by the turkey. So you have essentially a system that's looking at natural convection, okay? Or buoyancy-driven convection, all right? So there is a heat flow there. Okay? What did we do? How do we capture that heat? How do we capture the flux, the heat flux from the surrounding air into the heat equator? Anyone remember? Okay. How do we guesstimate what its effect was? You remember? Yes, Mia.
Seems like the prior.
So there was a difference, right? There's a difference between the temperature of the air, right? We were supposing the temperature of the air, and we had the temperature of the turkey, right? Now, if there's no difference in temperature between the turkey surface and the air surface, is there any heat flux? No, right? Nothing's going to happen. But then that's multiplied by a constant, which has the variable h, and that's the convective heat transfer coefficient. Okay? So you're right. We didn't simulate the fluid, right, around the turkey. That said, we did make some approximations so that we could essentially capture that behavior. And you had to fit an h, a heat transfer coefficient, and you had to, you had to pick a heat transfer coefficient, and you had to pick a thermal conductivity of the turkey to make everything cook in a reasonable amount of time. Okay. So we did, but we didn't. Okay? We kind of looked at problems that have coupled physics, but we've done some things to try to keep it in a single domain. We'll talk a little bit more about this heat transfer problem in a second. The same exact, well, a very similar problem. What about in this case over here? That was no heat transfer. In fact, if you look, when you put in liquid water, right, the specific heat of the water, the specific heat capacity of the water disappeared, right? There was, it was purely a fluids problem where we meshed. What did we measure on that step, though? The drag force, right? We measured the drag force. So, when you look at an airfoil, often you're not really thinking this is a multiphysics problem. Because you're going to try to assume that the amount of deflection that the airfoil experiences is very negligible and is not going to affect the flow. If it did, that could either be a very interesting problem or it could be very dangerous for whoever is flying in that aircraft. Okay? So what would happen though if instead of, and this was hashed before a few minutes ago, what would happen if that step were not rigid? What if it were a sea anemone, or whatever, like some squishy thing underwater that is flowing on? It could deflect, right? It could deflect. So what would you do to model that? Well, like it was shown before, because I forgot to erase it, you would have essentially the opportunity to create another mesh in that area and apply or provide elastic properties or viscoelastic properties for that material, and then you will be able to see it deflect. Now, if there's deflection, what happens to flow over the step? If that step changes shape, is that going to affect the flow? You betcha, right? Okay? And so technically what you would want to do then is rerun and go back and calculate the new flow based on that new geometry. Calculate the forces again on that solid, soft region. See how it deflects. Maybe it deflects a little bit differently than what you calculated the first time. Use that new geometry then. Calculate the flow again. See if it affects the flow. Hopefully it doesn't affect the flow that much. And then you call it good. All right? So that's what's called two-way coupling. When you have a flow or you have some type of physical phenomenon that then affects the properties of the other physical phenomenon, and then it goes back and it affects the original physics phenomenon. Okay? So we're going to avoid two-way coupling. Okay, we're going to do some fluid structure interaction a little bit later, but it's going to be one-way coupling. Two-way coupling gets very, very complicated and can be difficult to get to converge. Okay? Any thoughts, any questions on this for coupled physics? Well, we continue. So you could have some type of force, a literal force, stress over an area, or it could be like we talked about previously. It could be some type of heat flux, it could be a pressure. And these are some of the options that you might have in terms of the forces coupling. And then geometry. Geometry is another thing that can couple between the physics and then the properties of the materials. What happens to the viscosity of engine oil when it gets hot? Yes?
It decreases.
Okay, it decreases, right? That affects a lot of things, right? If you're designing an internal combustion engine. You want your oil to be a little bit warmer, so it's a little bit less viscous, so the pieces can move against each other appropriately. What happens if it gets too hot, though? Yeah, you could lose it, right? Or it could vaporize. Right? So the properties of fluids are very sensitive to temperature in many cases. The properties of solids, elastic properties, viscoelastic properties are also very sensitive to temperature. So there are ways in which we may have changes on the physical properties based on what's happening. Okay? So, going back or going toward this idea of fluid coupling to a solid, we're going to spend just a few minutes This is really horrible. Oh man, sorry. Okay, talking about what happens when you have a flow past the fin. And this is going to be a little bit of foreshadowing because this is what you're essentially going to be doing in your next lab. You're going to be looking at how much heat transfer you have between a fluid and a rod, a solid rod. Okay? So if you look at a textbook, Quem Prepare the Way, I have a citation on the next page, Quem Prepare the Way, that focuses on heat transfer. And there are a few of you who are taking heat transfer, right? All right, good. I'm glad to hear you got it. Okay, so in that book, you're going to see a lot of partial differential equations, just like you would see in fluid mechanics. And you're going to see a lot of solving for boundary conditions. And then you're going to see a decent number of tables. Okay? So there are a number of configurations in heat transfer. For example, a fin. So what you see here is a fin, and it could have some finite length. It could be infinite in length. Okay, it could have a convective heat transfer at the far end, at the tip. Okay, it could be adiabatic, meaning it's insulated at the tip. Okay, it could have some temperature specified at the tip, right? So that first one, you kind of say, oh, that's the A would be a Neumann boundary condition. C would be a Dirichlet boundary condition. B would also be Neumann, but with value 0. Okay, and D is, well, it's infinite in length. Okay. So what you have here, if you're trying, okay, so first of all, why do people care about fins and air and convection? Yes?
Get rid of heat.
Get rid of heat. Yeah. And what are some applications where you're trying to get rid of heat?
iPhones.
iPhones. Did you say phones?
Both iPhones.
iPhones.
Yeah, phones also.
Yeah.
Wait, what did you say first? I didn't hear it.
Like iPhones, like mobile.
iPhones, okay, mobile phones, yeah. All right, yeah. Your CPUs, your lawnmowers, your cars. Okay, what were you gonna say, Kira?
Oh, I do this, we're just listening to stuff on how to say spacecrafts.
Yeah, sure. That's radiation. Okay, but as it's going into the atmosphere, okay, or as it's yes, you have these wings that you could approximate as fins, and we have seen what happens when they don't have the appropriate insulation or there are holes in them. Things can happen. But in this case, right, or in the case that we're studying here, this is very simple geometry. Okay. Now, there are some things to keep in mind. So if we're thinking we gotta get rid of heat from an object, if you look at this gray and orange structure, typically, if you're trying to get rid of the heat from the solid gray structure, what is the temperature profile going to look like along the fin? So in this case, in the horizontal direction. What do you think that temperature profile should look like? I've got some, yes, go ahead. Okay, so yeah, so yes, so this is, and we'll call this X, that's the fin, right? And then I'm looking at X and T. What do you think that profile should look like? Yes? Right, okay? And this is, of course, assuming a few different things, right? So one, you have some temperature at the base, okay? So this is what people will call TB, all right? Okay, that's a temperature at the base, okay? And then if it's it depends on how long it is, and it depends on if you're specifying the temperature at the end of the fin, okay, or not. But more or less, it's going to go something like that. Okay, I'll do that. I think I want to do something more like that, okay? Now, what's going to affect that profile? We're giving up heat, right? So the base temperature is higher than the ambient temperature, right? We talked about this a few seconds ago. if the turkey is the same temperature as the air in the oven, there's no heat flux. There's no heat transfer between the turkey and the air to the turkey, or vice versa, right? So in this case, the ambient liquid is going to be cooled. Okay? What could affect this profile? Yes, Javier.
You need to start the temperature.
Aside from, okay, so sure, temperature can definitely, okay, so there's going to be, you have this T ambient, right? So there's, out here you have T ambient, and you have TB, all right? What other properties can affect the profile? Okay, so yeah, so if you have a fluid and you're like, okay, how fast is the fluid going? Also, what's gravity like? Okay, that could affect things too. You have buoyancy, right? We're going to simplify and we're going to capture that, like once again, in the convective heat transfer coefficient. Okay, so that is what we often call H. So H is convective heat transfer coefficient. And that has watts, that has units of watts per meter squared Kelvin. Okay, or watts per meter squared per Kelvin if you want. If you're using stamps. So it's power per area per temperature. What's the other thing that can affect that profile? So if H is high, right? If you have a lot of flow and a lot of heat transfer through convection occurring, which way do you think that curve is going to go? Okay, someone in quadrant 1. Haven't heard much from you all, although I guess you answered. But quadrant 1, heat transfer, the convective heat transfer coefficient goes up. What happens to this profile? You already answered. So yes, Muhammad Devin. Yeah, so it would do something like this, right? Maybe it ends up at the same. Depends, right? But it's going to come down steeper, right? Why is that? Because you got more air. It's flowing by faster. Okay? What happens when you take an ice cream and you stick it out the window of your car and you go fast? Is that going to make it stay solid longer or shorter? Unless it's like the weather we've been having lately, and now we don't, actually not today, right? Unless it's sub-0 degrees Celsius, right? You're not winning that battle, okay? I remember when I was young, they were like, hey, we gotta keep our ice creams from melting. Let's stick them out the window as we drive. Yeah, did not have a degree in mechanical engineering yet. Okay, so anyway, what's the other thing that can affect this slope, this profile? We talked about the surrounding liquid. What do we need to also think about? Yes. Yeah, properties of the fin itself, right? So radius could affect it, right? Yes. So the radius, if it's a pin, okay, which we're going to be using, or if you're thinking kind of the wetted perimeter, okay. So we'll call it P. P is in here. If you see, there's some P's here. All right. P is the perimeter. AC is the cross-sectional area. Okay, and K is heat conduction, or the thermal conductivity. Okay, so all these factors affect how that temperature profile is going to be, and they also affect the heat flux. See, this is the fin heat transfer rate. That's just a fancy way of saying heat flux. So look, if H is high, if the wetted perimeter is high, if the thermal conductivity is high, if the cross-sectional area is high, all those things end up increasing the amount of heat that you can whip away from your system. Okay? And you're going to get to kind of simulate this type of system. So I guess I don't have to, well, I guess I will, because I did make the effort to write out the code. So I took these equations and I took some values from Inker and DeWitt. This is for copper, so it has a thermal conductivity of 398, or about 400 watts per meter Kelvin. The heat transfer coefficient they gave us was 100 watts per meter squared. The temperature of the fin base was 100 degrees Celsius. The diameter was 5 millimeters. Okay, and then you calculate, and then the air temperature was 25 degrees Celsius. And this, I used this for the infinite fin. Okay, so the fin actually goes forever, but in their book and in this example, I only went out 30 centimeters. Okay. And with those values, this is what that profile is. All right? So you've got something you could do a design with if you wanted. This is not truly coupled in the sense of I'm not solving Navier-Stokes equations to be able to then figure out what the heat transfer coefficient would be to then figure out what the profile of heat might be. But if you want, okay, here are some of the differential equations. Just plugging this in to one of the generated AIs, okay? Simple problem. How do you couple the PDEs between fluid flow and heat transfer for a multiphysics simulation? That's all I asked it, okay? And it looks right. So what you have are Navier-Stokes, where this is we have a continuity, right? We have the momentum, and we have Navier-Stokes. This thermal term they call a buoyant term. I actually cut that out because it's a little bit, I didn't want to go into that, all right? But that's this term that they have here, even though they already have a rho g here, they say there's a flow that's induced, so that's a little bit questionable, all right? The heat transfer, this is the heat equation, right? This would be some internal heat source. This is Fourier's law right here, the divergence of that, okay? And this is essentially rho c dt dt, right? So that's the specific heat times the density, or it's the heat capacity, and times the change in temperature versus time. And then this term is a flow term. So this is an interesting term. This is where, if you see, okay, if I have a lot of flow, all right, that means that it's going to take a different amount, it's going to affect the amount of time it takes for this system to heat up or cool down, okay? And then if there's no flow, no advection, all right, then this term goes bye-bye, all right? The flow, right, this u dot the gradient of the temperature, this affects heat flux, and they make some good points. The neural networks, the the language models. They make some good points. Look, the density is dependent on temperature. The viscosity is dependent on temperature. Okay, thermal conductivity is dependent on temperature, right? So you would have to keep track of all those things. And then at the interfaces, we can say, and this is, you got to be a little careful here, but what they're saying is that the fluid temperature at the surface of whatever it's going over is going to equal the solid temperature at the surface. Okay? And then, hey, it's Fourier's law again. All right? So this is saying we've got the heat flux between the two systems has to be the same. Between the fluid, the heat coming into the fluid has to be the same as the heat coming out of the bar or the fin. Okay? All right. So you might also ask yourself the question, should I really couple? The couple or not the couple? Okay? If you can avoid it, avoid it. All right? So if one phenomenon has much higher values than the other, then you can forget about it. All right? But if not, you have to keep, well, that's a little unfair. If you can simplistically model one of your physics and then use that as an input to the other one, that's nice. Right? That's the more convenient way to do it. If not, then you have, and if you cannot, and for example, well, we're doing an example with flow over a heated rod. By using fundamental principles for the viscosity and the density of and the heat capacity of the fluid, you can try to essentially approximate and not, you don't have a heat transfer coefficient for that particular system. You can try to run the simulation. But often, you're going to want to try to avoid having to simulate more than is necessary. Professor Singer has this nice chart that we're going to go through kind of briefly. Okay? Well, maybe not. That's maybe not that briefly. Okay, so what we have here is a column of physics, thermal, fluid, solid, electromagnetics. And we have a row of physics. And we're going to say, how does the column, this is a column, but how does this row, so how does this item affect or cause something on this item in this column? So we're going to do row column, where this is row, this is column, row is beating up on the column. Okay, so how do thermal effects, how do thermal physics affect thermal physics? Sure, Joe. Let's go over here. I can't remember your name. Yes? Hugh. Again, thanks, Hugh. Okay, so what do you think? How do thermal physics affect thermal physics? So say that again, the last thing, temperature difference is what? Yeah, okay, so good. So temperatures, so we're going to say that this is more of a property category. So, for example, thermal conductivity, as you were saying temperature, right? Let's say that thermal conductivity is a function of temperature. So that's going to affect the amount of heat transfer you have, right? So this is conductivity. And there could be other effects. Heat capacity. can also be a function of temperature. Okay. Okay. How can a thermal system affect a fluid system? So now we're in this box. Yes, Guavier.
How high is the temperature, the level part is to affect how fast or how slow it's going?
Yes. Okay, so you can have let's say that is something in terms of a couple of things. So thermal can affect density, which can affect buoyancy. Okay? Right, if I heat a gas up, it becomes less dense. If I heat a liquid up, it can also become a phase change, right? And that can affect flow. All right? We mentioned this earlier. Thermal can also affect viscosity, right? So that will affect a number of behaviors. And when we said, buoyancy, that means that you have induced flows. You could have boiling. You could have phase changes. There are a number of ways where a thermal system can beat up on a fluid system. Okay, how can a thermal system beat up on a solid system? How do thermal physics affect solid mechanics? Sure, Hugh? Okay, all right, so yes. So you could have phase change. What are some of the properties that can be influenced by heat? Yes.
Get strengthened or weakened with air.
Okay, so so let's say SU, the ultimate tensile strength, is dependent on temperature. The elasticity is also dependent on temperature. The Poisson ratio is also dependent on temperature. Do you remember when we did this fun example where we put a bar between two fixed walls? Yeah, right? So you have also the ability to induce forces based on the coefficient of thermal expansion. All right, electromagnetics, we're mechanical engineers, so I'll just do this quickly. So you can affect the permittivity. So this affects electrostatics. You can affect the resistivity. Okay. You can actually also affect yes, it's mu, but it's permeability, magnetic permeability. This can be an issue in motors. Okay, if you heat your magnets up, or if you heat up your cores, they can affect the permeability, which can cause problems, or just cause changes. Okay. All right, how can a fluid system affect a thermal system? We just did this ad nauseum, right? Maybe it was an ad nauseum. I'm glad you're not nauseated. It'd be nice if you were awake. No, but yeah, how does a fluid system affect thermal systems? Sure, Q. Right, so convection, right? Heat transfer. Okay, you have a flow. you could be transporting a hot liquid and a cold liquid. You could have a heat exchanger. All right? You have a cycle. Your refrigeration is based on a phase change, right? Where you have a compressor taking a gaseous form of refrigerant, compressing it down back into a liquid. It passes by some type of warmer surface, whoop, sucks all that heat in, phase changes, we repeat, right? So refrigeration is a good example here. And heating is a good example too, right? We have convective, so we got both. All right, how does a fluid system couple into a fluid system? Anyone ever watch Back to the Future? Old movie. So George McFly is trying to make a good impression. And instead of saying, "You are my destiny," he says, "You are my density." All right? So pressure can affect rho, right? The density can be dependent on the pressure. That's one way. Properties can change. You have also, you have interfaces and phase changes between gases and liquids. All right, so that's another way that this can be coupled. All right, fluids on solids. Yeah?
Phase change.
Okay. Yeah, I guess so. If you lower the pressure enough, you're going to boil. Okay, sure. But I don't know about that. I can put a solid in. I don't know. There's like some weird. That's okay. We'll give it to you though. Yeah, I'm gonna put a question mark there. Okay.
Okay.
All right. How else? Some of you will probably be making a lot of use of this over spring break. Yes. Exactly, flight. This is how you fly, right? So you have aerodynamics. It was Jesse, right? Okay. Did I call you Josh? Justin? You're Josh, right?
Yeah.
Sorry. Okay.
I didn't even hear it.
You didn't even hear it? Okay. Yeah, so that's one way that this can happen. You can also induce stresses, right? You have submersibles, right, that are going to be under a lot of hydrostatic pressure. So you have hydrostatic loading as well. Dams. A lot of different ways this can happen. Okay? I think we're going to stop. You get the idea, right? You got the idea? You covered the principle? Okay, good. And so there can be a lot of coupling and they can go both ways. When I say both ways, you can have, for example, a fluid thermal and thermal fluid. They can go both ways. They can couple with each other like this. Those are some prime candidates. as are also fluid-solid and solid-fluid. Pistons, for example. All right. Let's change gears a little bit. I thought I may struggle with this, as with many things, but I threw in a few bits about residuals. Okay, so for residuals, you saw them, right? When you did the first assignment, let's see if ANSYS will cooperate with me. It's always a risk, always a risk. Okay, so this is the same example that you were working on with the backflow over the step. You can do it. Move very slowly. I'm being patient. I'm hoping. Okay. It just needed some mysterious second click. I'm sure you've experienced this already. Okay, so I'm going to initialize and calculate. And look, that this thing is plotting these scaled residuals. All right, it worked. Did anyone ask themselves, what in the world is going on here? Yeah? Besides it looks kind of cool? Okay, so we're not going to get deep into the theory here. But these residuals no. Where did I lost it? Oh my goodness. There we go. I lost it. There we go. Nope. Sorry. There it is. Okay. Under the monitors, you have the option to set criteria for what's happening. Now, we will talk briefly about turbulence in more detail. Okay. The K has to do with kind of the amount of turbulence you have. Omega has to do with how that turbulence is being dissipated. It's the K omega turbulence model. It's a Reynolds average Navier-Stokes equation or method. All right, but the first three that you have a basic idea. Okay, what those mean. Continuity has to do with is mass being conserved. And we talked about the finite volume method a little bit, and how we have mass coming in and out of the element or cell. You know what x velocity, you know what y velocity are, okay? And so the default values are often pretty good. What we're looking for in these values is some type of decrease, right? So let's just say, before I say anything that's really wrong, okay? If you're really interested in seeing how things work with ANSYS or other finite element, actually, well, this is finite volume, sorry, or another numerical analysis software, you can take a look at they have user guides. COMSOL has documentation as well, extensive. And they're available. So we were doing pressure-based solver. Okay, if you go back in here, at the very beginning, okay, we're doing a pressure-based solver. It's not that important for what we're talking about here, okay? So we are having, it's unless you have requested others. Well, the default for our fluent is more than just a mass imbalance, okay, which would be related to continuity, okay? And the idea is these values, or these residuals, okay, represent losses or gains that you shouldn't be having. That you shouldn't be having with velocities with different parameters, right? So you know that if you have a certain inlet velocity of a certain area, there's got to be a certain amount flow that's coming into the system, that has to be going out of the system. And then if you look at the individual cells, you have to have the flow coming in and the flow coming out be close to zero in order for you to be satisfying your convergent criterion, your convergence, right? So these are akin essentially to those Riemann sums on the surfaces and the flows that you saw, okay? You have in, out, and then you could have a term that is providing maybe an internal flux or something of that nature. Okay, so this is like it says, this is how you monitor them, like we just showed. Okay, and at the end of each solver iteration, the residual sum for each of the conserved variables is computed and stored, thereby recording the convergence history. This history is also saved in the Okay, on a computer with infinite precision, you would have these residuals going to zero. Okay? So that's how the solution converges. On an actual computer, which is what we're using, okay, the residuals decay to some small value. There's some round off, and then they stop changing. They level out. Okay, for single precision, so you might not have been looking, but when I opened up, for now, I was using single precision. Later, we'll use double precision, and we'll use more cores. Okay. But for single precision, it says these values of to the 10 to the minus 3 are just fine. And then maybe you might go down to 6, 10 to the minus 6. You might use 10 to the minus 6. You're not really going to put down 10 to the minus 12 for most problems, even when you go to double precision, at least for this class. Okay. But the idea is that you get to specify when enough is enough. When the errors that you have are below what they should be. Okay? When you're conserving the quantities of choice. So, what is changing? You know, to make these errors, these residuals change. What is ANSYS doing? What is it doing as these values are going down? And maybe it's helpful to say, wait, how many of these jumps are there? Well, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does that number sound familiar? 10 is a really interestingly not random number. Well, remember? Well, I wouldn't expect you to remember. We said we were going to do 10 time steps. This is a transient simulation. We're running it for 1 second. And we're doing 0.1 second intervals. That's what we're recording. That's like the I record in the finite difference method that we were using, right? But what do we do in between the I records? We play with the time step. Well, sometimes we play with the time step, right? We get trying smaller and smaller time steps. So what's happening is you have this K matrix that's been set up based on the space. I misspoke in the other class. The K matrix is not, unless you're remeshing, which is one technique, all right, but that can be slow. Unless you're creating a new mesh, the K matrix is essentially staying the same size. That's my understanding. You can fact check me on that. I said it was changing in size. What's happening though is the time step between the specified time steps that you gave it, that's going to be changing in size, right? So the computer is essentially saying, oh, 0.1 fine, let me try a first shot of 0.1. What's my error? Oh, too much, don't do that. Okay, let's try 0.05. Oh, maybe too much, okay. 0.01, right? It keeps going until it gets to a conserved residual. So, I just wanted to point that out. When you talk about convergence in your reports, it's okay to put in one of these plots, these screenshots. I understand that. But that is not the only thing I want to see for convergence. If that's the only thing you say and it converges, you're not going to get high marks on the convergence one. You've got to do something else. Okay? Because if you're running this, you can discretize the mesh. Fine, well, fine. Okay? And you can look at how the mesh affects the answers, right? Here, ANSYS is really kind of taking care of the time. But the other thing you can do is you can reduce the residual threshold. If you want to play with time, you can say, you know what? I'm not sure if 0.001 is a low enough residual. I'm going to decrease my residual to 0.0001 and see if I can still get the same result. Okay? So there are additional things that you can do, and when you start looking at, a final value like the drag force on a step, there are a number of things that can affect that result. Okay. You gotta love the art of numerical simulations. Would someone read that first sentence? Or the first couple sentences there? Any volunteers? Okay, Kira, go for it.
There are no universal metrics for judging convergence. Residual definitions that are useful for one class of problem are sometimes misleading for other classes of problems. Therefore, it is a good idea to judge convergence not only by examining residual levels, but also by monitoring relevant integrated quantities such as drag or heat transfer coefficient.
Okay, so, right, you don't just look at these residuals, we are going to be looking at convergence of our specified quantity of interest. Okay? And there are no universal metrics. So there's a little bit of art to this and a little bit of experience. Okay, so that's what I wanted to say about residuals. So now hopefully you have a little bit better idea of what's happening when you see that nice little and there are going to be times when it's not going down and it goes up. And you're like, oh man, and you're like, please turn around, please go down. And then it explodes. Then you gotta figure out what's going on. Alright? So you will see. Verás. Okay. Let's talk about writing just briefly. Okay. Here. This is the weighting of the sections in your final paper. Okay? So you abstract, you're trying to get 30 points. Which section is the most important? Results and discussion. Okay? So please make sure, and John Singer, he had 3 points for results, 10 points for discussion. Okay? They're merged here. You get 5 points for references. That's a huge percentage. And yet, most people mess it up. Okay? Please just put at least 5 references in there, a few academic journal articles. If you have more than a couple of tutorials, more than a couple of whatevers, 5 references is not hard. And format them correctly. And cite them in the paper. Okay? So this is not the PowerPoint presentation when you just do all this work and at the end of the presentation you put your references. Right? This is, you cite them as you need them, as they're relevant in the paper, and then they should appear in the end. Okay? You do those few things, those are gimmies. I just look. I'm like, okay, they put their citations in, The number of citations in the paper is the same number as the citations they include in the references. They don't look like garbage references. 5 points. Okay? So, as you're working on your preliminary outline, keep those things in mind, and you can read these slides later if you like. Okay. Again, please use a reference manager. Okay. For the preliminary outline, okay, you've got to submit responses in the form, and I just need one link somewhere, somehow. Okay. And then for now, you do not need an abstract. You need no conclusions and no references for what's due on the 23rd. Okay? But we do want you to have a little bit about the baby step. Yes, what do you put in results in discussion when you don't have results in discussion? Well, put a hypothesis in there. Okay? We do want this to be hypothesis-based as well, right? So please, put your hypothesis, say, the hypothesis is this. Be so blatant, and you get instant bonus points, all right? Because you psychologically helped me. Because this is a painful, painful thing to do, to read these papers. It's wonderful too, but it's really painful. Okay, that's where we're going to stop. Okay, if you want to talk about your final project, that's great. For the attendance, the code is 1, 2, 3, 4, 5, 6. There you go. And you can take a picture of that screen. It's white. Do you get that? The code is 1, 2, 3, 4, 5, 6. Yes. What's that? No, that's an old one. We're just doing the white one. That one has the date from 2025 on it. So it won't, this is me, what is it, frankly? It's me, oh, I didn't shut off the thing. Oh well. Fine. But yeah, it's me being behind again. All right, I'll go ahead and stop the video and we can talk about your projects. Oh, you're still taking